Hello, everyone. Thank you for being online and attending to this event. My name is Alex. A few words about myself as a start. I've been researching x86 platform security for quite a long time. This work covers subjects like Intel Management Engine, Intel BootGuard, and UEFI biosecurity. Today we're going to talk about issues in low-level Intel architecture components such as microcode, authenticated code models. We'll see how these issues can be discovered and exploited. And also we'll talk about possible mitigations for such attack surface. Let's start with CPU roots of trust overview. Every modern Intel CPU has processor cores, the bootstrap processor, which starts when powering on. This core begins executing the start instructions in firmware when CPU is released from a reset state. The application processors, which are started by bootstrap processor, when ready and needed. An optional graphics core, an integrated memory controller, and a level 3 cache, which is shared between the cores. Also, CPU can contain some input-output logic. Each core has a read-only memory containing the CPU microcode, which is programmed while manufacturing the device. And this is our first root of trust. Control unit, after each powering on, loads this microcode into a faster and rewritable memory called control store. What is a microcode? Public sources tell us this is a program written in a hardware level instructions to implement higher level instructions. You can see an example of x86 MOVES instruction implementation here. The thing is, and it is well known for years, the microcode can have bugs, whether these are security issues or not, so it should be updatable. Remember, the original microcode is stored inside the CPU and in non-updatable memory. Hence, the updated version of a microcode should be replaced in the control store every time CPU is powered on. And you can notice such updates are included in system firmware. As you can see here, there's a firmware interface table, FIT. They contain entries pointing to microcode updates. Please note the updates are CPU model specific. Obviously, the FIT is a part of system firmware stored on SPI flash memory. You can see a common image structure here. There's a pointer at the end of the BIOS region pointing to a FIT. This is how modern Intel CPU could find and load microcode update in an automatized way before execution of BIOS. What else do we know about FIT? Well, it had started to be a required element for Intel architecture since introduction of Intel BootGuard technology. Because it contains entries to point to BootGuard components, allowing the CPU to verify the integrity of the BIOS image before executing it. Also, like I told before, FIT is used to update the CPU microcode before running any firmware and before starting even Intel BootGuard. Now let's see what a microcode update binary looks like. It starts with the main header containing such fields as a version, date, CPU model code, a processor signature, in other words, checksum, etc. This header is followed by an extended header. This is an extended header structure. Seems like a common Intel signed binary structure also used in Intel CSME firmware, for example. It also has fields like version, sizes, processor signature, security version number to deprecate loading of downgraded versions of the microcode once the given version is loaded, of course. Also, this header has an RSA public key and signature, allowing the CPU to verify the integrity of the microcode update before loading it. The hash of a public key is hard-coded into the CPU, and based on my observations, it can stay the same for a few CPU generations, and even for production and pre-production debug versions of platforms. The microcode update body is unfortunately encrypted, so almost no one actually knows what else the microcode is capable of, besides some startup behavior like microcode updates loading or Intel bootguard. By the way, a few weeks ago, the decrypted microcode image was dumped from Apollo Lake system on chip using GTAC through Intel DCI. It could be used as a start to research its contents. Here are some collection of facts about microcode implementation. Like was told before, it implements CPU instructions. It configures the execution logic on the line. That's how bugs like side channels are fixed. It implements some startup behavior like fit parsing. This is how it can load microcode updates from fit. It loads and executes Intel authenticated code models. It could be used, they can be executed from FID or not. A few words about ACMs. These are signed and sometimes encrypted Intel code models with a similar structure as a common Intel common binary header. They are loaded into a shared level 3 cache, I guess because the drum is not trusted. By the way, some public sources call it ACRAM. Authenticated code RAM. These models executed from there only by bootstrap processor. Other cores should be sleeping. They serve as a root of trust and as an implementation for such technologies like Intel bootguard, Intel trusted execution technology, Intel BIOS guard, also known as a platform flash armoring technology. Quite interesting note is the BIOS guard, ACM, and microcode update binary are both encrypted and signed with the same key. So now we can see all CPU roots of trust in a single UEFI BIOS image. It is fit, microcode updates, Intel, and all of the ACMs I mentioned before. Let's talk about the ACM for the earliest platform boot phase, Intel bootguard ACM, and its issues. As you can see on the picture, the blue area is protected by Intel bootguard. The ACM verifies its integrity before executing the BIOS. So in case you somehow manage to modify the system firmware, making changes to this area will end in the system refusing to boot. However, the FIT microcode updates and the ACM itself are placed in an unprotected area in most of the systems, and we can replace them with older versions. So what can be achieved by that way? To find this out, let's look at the ACM header format. We have already saw something similar today in the microcode header structure. We see here a chipset ID field, which is always 0, a build date, security version numbers, and RSA signature with the key to verify it. What do we know at the moment? Intel bootguard ACM is a 32 kilobytes binary. The hash of RSA public key to verified signature is locked inside the microcode. This should protect from running older ACMs on newer CPUs. Security version number also should protect from downgrading the ACM. This is how it should work. And this is the reality. The key for signature verification hasn't changed for years. Today in 2020, they use the same key for signing Intel ACMs as did since the introduction of the Skylake architecture. You can say, but they have security version number for this purpose. And I will say, here's the reality. This number changes very infrequently. A few ACM versions in a row can have security fixes applied without increasing the ASVM. Binary diffing helps perfectly to reveal the patches. And here's one I found in versions signed with the same key and having the same security version number. Here's a 2016 version of Intel bootguard ACM. You probably know this ACM should verify 2 key manifests describing the integrity of UEFI BIOS image. And here is the code parsing the first key manifest. As you can see, an RSI signature checking routine is invoked. So let's look into it. There was an issue in this routine an RSA public key model on the next key manifest is verified, but the public RSA exponent is not. This allowed performing attacks on RSA signature by replacing the public exponent with a small value. In 2017, that was fixed. They added a flag in case it is true. Both the RSA public models and exponent are verified. But after fixing these issues, they haven't changed nor RSVN, neither the signing key. This opens the way to replace the ACM with the vulnerable 2016 version and attack Intel Guard verification procedure. The next interesting case is downgrading Intel TXT ACM. However, since this is not a startup ACM, it is not pointed by FIT, this should be done in runtime because it could be protected by bootguard. To do this, firstly, let's see how the CPU could be tricked to downgrade the microcode, because this is an important step. What do we know about the microcode updates? They are to improve stability, performance, and apply security fixes. A very important note is updates should be loaded each time CPU is powered on. I mean, after sleep, hibernation, or full shutdown modes. I've been watching that far not always updates are loaded by CPU via firmware interface table. This is because in case the update requires something special like initialized drum, which is not available on FIT as part, or it has to be loaded by the BIOS manually as early as possible from the moment conditions are satisfied. Also, probably the FIT is not always parsed while leaving sleep or hibernation modes, might be performance optimizations. This is why you can always find a microcode update loader, a legacy microcode update loader in a modern BIOS. Another very important note is that updates should be loaded onto each core separately. The legacy microcode update loader looks like this. It uses some MSRs, machine-specific registers, to update an input microcode. To check the CPU update version, another MSR can be used. Besides the above set, what BIOS does to load the microcode update? Firstly, the CpupEI model finds the appropriate update, one of the most actual and supported by the installed CPU. Secondly, it copies the update from the mapped SPI flash memory into physical memory. The physical address of the update is stored into a handoff block. This is just a UEFI by specific structure, never mind. A bit later, the PlatformInit model will find this hop, retrieve the microcode update buffer address, and start a microcode update loader to apply this update. Please note that all of these actions are performed during the normal boot. What else is done? Later, system management mode code also finds this hop, retrieves the microcode update saved address, and copies the applied microcode update into SMRAM, system management RAM, probably to protect it from being replaced or damaged by an operating system. Finally, the SMRAM address of the applied microcode update is saved into a UEFI variable called int ucode. An interesting note is this variable is accessible both from the boot time and runtime environment, meaning it could be fully accessed from an operating system. As you can see, these actions are performed to optimize performance for waking from sleep mode. In other words, after the system was put into sleep mode and when waking up, the CpupEI model, instead of searching for the microcode update again, it gets the pointer from the int ucode UEFI variable and saves it into a hop. And then the update operation repeats. The PlatformInit model finds this hop, retrieves the microcode update address, and updates the microcode with it. Here's an obvious way to perform a downgrade attack. We can load an old microcode update image into physical memory. We can make the int ucode UEFI variable to point to it, and we can perform sleep wake-up cycle. The system will be booted up with an attacker-provided microcode if it's valid and passed the integrity check, of course. Here is an RW everything screenshots, the 2019 version of the microcode update update, and after performance, the above set actions, the 2018 versions is actual for this CPU. There are a few consequences of this attack. The first and most obvious one is removing fixes for side channel attacks. This could open ways for researching. But if we talk about security incidents, most of them are extremely hard to perform in the wild and have never been spotted. However, there's not much available detection tools. If you still want to know more about these attacks, please refer to the detailed analysis referred here. Another interesting case is to unlock platform debugging capabilities. My experiments showed that older versions of microcode has no anti-debug mitigations. So this technique could be useful for those who use dynamic analysis in platform security research. The good part is that ACM authentication is performed by a microcode. Probably the microcode is directly binded with the specific ACM versions. The microcode update might know the hash to verify the public key of the ACM or SVN of ACM. Anyway, the older versions of microcode support, in other words, does not deprecate loading of old versions of ACMs, which are also updatable firmware component and can have security issues. Hence, downgrading microcode allows to load the downgraded versions of ACMs with an exploitable one-day vulnerabilities. This obviously compromises the technology dependent on the ACM. Well, again, Intel Debug, a technology for firmware integrity verification. The ACM is not encrypted, so binary diffing is applicable to find 1 days in these ACMs. It's executed only on startup and does not execute it while waiting from sleep mode, except each 12 boots. I guess this is all about performance optimizations. So there's no point in attacking ACM through the microcode update here. Usually, while thinking about searching vulnerabilities in Intel Debug, the implementation of a vendor part of trusted boot is a target. Now Intel Bias Guard. This is used to disable unauthorized write operations to SPI flash memory where the firmware is stored. Its ACM is encrypted and it's extremely hard to find a fixed issue. This requires a lot of time for testing its behavior, and this is a huge subject, so we won't talking about it today. Now about Intel TXT. This technology allows to verify the integrity of some runtime code. Async ACMs is usually a target here. It is not encrypted. It is bigger than Blueguard ACMs, so binary diffing allows to find 1 days in these ACMs. And some of the vulnerabilities in these ACMs were already described in public. And the full attack scheme will be looking like this. We will place a microcode update in memory. We will replace an TXT ACM and make the int code variable to point to the old version of the microcode update and perform the sleep wake up cycle. However, there is a problem. TXT ACM has also an SVN, and to bypass this check, we have to rewrite the ACM while waking up from the sleep mode. So S3 boot script could help us to do that. The boot script is a table of operation codes which should be performed while waking from sleep mode to restore the platform configuration in a faster way instead of running the normal boot path. One of the system management mode code models has a perfect interface for making changes to S3 boot script from operating system. It parses an input data from a caller then it will take some time from this input, some data from this input structure, and place it into a bot script. As you can see, we can add a memory write operation codes into it. This allows rewriting a memory from S3 boot path, and hence this could allow to replace a TXT ACM in memory while waking up. So what about possible mitigations of these attacks? One of the obvious thing is Intel SJX. However, it doesn't check the microcode SVN when leaving sleep mode. In other words, waking up. So most of the mitigations could be applied only by platform and BIOS vendors. One of them is to the better usage of SVN values. Also, BIOS vendors can protect into code UEFI variable to mark it as a read-only and close it from runtime access. However, this could be bypassed if an attacker manages to run an arbitrary code in SMM, because the NVRAM area where this variable is stored, it is rewritable by architecture. Also, we can make an operating system to update the microcode to the latest version. However, this process could be already compromised at the moment of validating the update version. So the better way to mitigate from these attacks is to supply only the microcode updates that could be loaded from FIT. So in an automatized way, this will deprecate usage of legacy microcode update loaders, and such attacks could be impossible. So we can see a supply chain problems here. Most of them is a disadvantage of security through obscurity model. The problem, we can see that the problem in a basic component compromises all technology it serves as a root of trust. And after analyzing some issues, some fixes for such issues, we can see that firmware vendors aimed to protect code integrity, and however, they still forgetting about other attack vectors, such as data-only attacks, for example. So thank you for listening. You can ask questions, and I will answer them. Thank you.